Okay, hi everyone, welcome back. So this is the sixth and final video on regression diagnostics and how to check various assumptions when you're fitting a regression model. And in this video, I'm going to focus on leverage and influence tests. So just as a quick recap, what I have done, scroll up, what I've done in the previous 5 videos is working with the MT-CARS dataset. It's a small dataset, 32 observations. Each observation represents a model of car, and then some information, performance information about such as MPG, weight, things like that. And I use stats models to fit this really basic multiple regression model where we used weight and displacement to predict miles per gallon. What we found was that weight was a significant predictor of miles per gallon. So the heavier a car, the lower the miles per gallon. And when I've conducted a series of diagnostics based on the model, so we've looked at normality of residuals, linearity between the DV and IVs, multicollinearity between the independent variables, homoscedasticity or constant variance, and independence of error terms. And now we're going to finish off by just talking about leverage and influence tests. So data points that have values that are very different from the majority of observations in a data set are said to have high leverage. Influential data points are those that have values so extreme, such as outlier scores, that their removal from the data set would cause a significant change in the estimation for the regression model coefficient. So it changed the slope of the regression line essentially. So there are 2 tests we can use to find outlier points that may have high leverage or influence in our data. So we can use Cook's distance to assess which points are univariate outliers, these being a point that has high influence on only one of our independent variables. And we can use the Mahalanobis distance to evaluate whether any points are multivariate outliers. So these would be points that have extreme or high leverage scores on more than one of our independent variables. Okay, so we'll demonstrate that here. It's going to require a little bit of coding, but we'll do Cook's distance for univariate, and then we'll do Mahalanobis distance. So firstly, I'm going to obtain an influence plot using Cook's distance as the criterion. So this influence plot, it comes from it's from stats models again. So I'm using matplotlib. So creating a figure, it's sm.graphics.influence_plot, and I'm passing res, which is our the object that saved our regression model results, and I'm specifying the criterion equals Cook's passed as a string. And if I run this, what you will see is we've got this quite interesting scatter plot of data points. So let's put that there. In the above plot, high leverage scores are plotted along the x-axis. Yeah, so the fact that a number of data points are towards the higher end of the x-axis, so up here, scale, it indicates there may be quite a few data points that have high leverage scores. The size of the blue dot provides an indication of their Cook's distance. So larger dots indicate a high Cook's distance, suggesting those points are likely to be univariate outliers in our model. Okay, and so you can see there are a number of these data points that are kind of quite large and to the high end of the x-axis scale, and we would want to investigate this further. So in addition to using this particular plot, we can use the function .get or method get influence to assess the influence of each observation and compare them to a critical Cook's distance. Okay, so what I'm gonna do here is I'm going to calculate Cook's distance and the critical value that indicates which scores are univariate outliers. Okay. So first of all, we're going to create this object called results_Cook's D for Cook's distance, and we're going to take our results object, use the get influence method, and the Cook's distance. We're going to look for the Cook's distance. Okay, and then I'm going to basically just I want to know the length of the data frame. We kind of know what it is anyway, but this is how you would code it. To get the length of the data frame will give us the sort of n value. and that's going to be equal to the length of our data frame, and we're looking at weight here, so we're looking at the weight variable. Okay, then I'm going to calculate the critical Cook's distance. I'm going to save that as critical D. Okay, and that's equal to 4 over n, and then I'm going to print what that is. So I'm going to print critical Cook's distance and then print out the value that this returns. Yeah. Okay, so we're then going to identify potential outliers with leverage. So what we're going to do is look at outliers, outlier distance, and we're going to set that equal. So this is a new object, and that basically what that will return is anything from our results for Cook's distance that's greater than the critical value. Okay, and then the last thing I'm going to do is actually output potential outliers. So I'm going to print the index of these outliers in the data set and also the Cook's distance, essentially. So we're going to see two things printed out. One's going to be the critical value of Cook's, and the other is it's going to select and print out anything from the data set that is a univariate outlier and tell us where in the data set that sits. Okay, let me run that and you'll see. So we've got a critical Cook's distance of 0.125. So anything with a Cook's distance larger than this is going to be a univariate outlier. And it's found for essentially, so entry 16, so observation 16, 17, 19 and 24. And you can see there Cook's distance is there, 0.34, it's bigger than 0.125, 0.14, bigger than 0.125, 0.18, bigger than 0.125, 0.13. 3 bigger than 0.125. Okay, so it's given us, what this has done here is given us our critical value for Cook's distance, 0.125. It's returned data points with a Cook's distance greater than this, and so we know which are univariate outliers. So they exceed that critical value, and that's provided to us in two lists. The first showing the index of the data point in the data set, the second giving the actual Cook distance for that data point. So we can see we've got 4 data points that have a Cook's distance greater than the critical value, and we could consider these to be univariate outliers. We would most likely want to remove these data points and then run the regression model again. Okay, so we've assessed univariate outliers, but what about multivariate outliers? So next what we'll do is we'll consider whether any of our data points are multivariate outliers by assessing their Mahalanobis distance against the critical value. So to do this, this is going to require me creating a specific function, manually creating a function to do this. Okay, so first of all, I'm going to create a new data frame containing only the variables in the regression model. So I'll call it data frame 2, and we'll just include MPG weight and displacement. Okay, so there it is if we look at the head of it. And then this function I'm creating, so I'm defining a function called Mahalanobis. I'm giving it that name, Mahalanobis, and I'm telling it what parameters it should take. It should take an X variable, data, and some measure, some covariance kind of measure. So I won't go into too much detail about this, but there's a couple of things that we're doing here. We're working out X mu, which is going to be the mean, which is going to be each X value minus the mean for there. So if we take each X variable, take each observation, we subtract the mean from that observation, and we're going to do that calculation on whatever data we pass in here. The data we will pass in is going to be our data frame that we saved up here. If not cove, then we're saying cove equals mp.cove data values.trace. So we're basically getting a transposed covariance matrix, and then we get inverse covariance matrix is mp.linalge.inverse of the covariance matrix. I'm not going to go into too much detail about this, but so we're kind of using linear algebra functions from NumPy here. And what we're going to get at the end is we're going to get a Mahalanobis value. Okay, so let me run this cell. When when we call the function, that was what it will give us. So what I'm going to do now is create a new column. I'm going to append a new column to our data frame called Mahalanobis. And that's going to give, for each value in our data frame, for each entry, for each observation, give it a Mahalanobis distance. Okay. And I'm going to do that by using this function we created up here. So I'm going to pass as the x. X is going to be our data frame 2. Our data is going to be data frame 2, and we're passing these 3 variables. Okay, so let me run that, and I get this error message because it doesn't like the way I've done it. It kind of telling me that in future versions this type of thing will be deprecated, and I should probably use the .log method instead. But if we look, this should have worked. So there we go. Yeah, so it has worked, and it's appended a Mahalanobis distance for each of our observations in the data frame. Okay, so we've got a Mahalanobis distance, but we want to know which ones, what that means, which ones are actual multivariate outliers. So we can calculate a p-value for each Mahalanobis distance, and if it's significant, if we've got a significant Mahalanobis distance, so a Mahalanobis distance with a significant probability attached to it, then it's a multivariate outlier. So I'm going to create another variable and append it on the end here called Mahal-P for the Mahalanobis p-value. And to work that out, I'm going to do 1 minus stats.chi-square.cdf, so a cumulative density function, and we're going to pass in as an argument this kind of Mahalanobis variable. Okay, let me run that. Probably get an error message again here. Yep, didn't like that either, did it? But if we then look at df2, it's given us p-values that we are interested in. So there's the whole data frame printed out there because it's quite a small data frame. And what we can then do is look through. It's easy to do because we've got a small data frame here. Look through to see which of our Mahalanobis distances are significant. Looking at the p-value. So what I've done here is I've created a function to calculate Mahalanobis distance for each of our data points. I've then used the SciPy stats.chi-square distribution, cumulative distribution function, the CDF, to calculate the p-value for each Mahalanobis distance. Those that reach a statistically significant p-value, so p is less than 0.05 in this case, we could consider them to be multivariate outliers. So they're outliers on more than one variable. Okay, because we've only got these 32 values observations in this data set, we can inspect the whole thing without filtering for values below p is 0.05, and it appears like we've only got one multivariate outlier. In this case, which would be row 16. It's got a Mahalanobis distance of 8.74. P is equal to 0.033, say. Okay, so that looks like our only multivariate outlier. Okay, so we've had 4 univariate outliers and 1 multivariate outlier. Okay, so that's it. Leverage and influence. Cook's distance and Mahalanobis distance. So just to summarize, this is the 6th video on regression diagnostics and assumption tests. It's the last one I'm doing on this. But I've covered the different, in all 6 videos, I've covered the different assumptions, data assumptions that need to be met in order to conduct a simple linear or a multiple regression analysis. And what I've done is I've kind of demonstrated how to check the assumptions for regression using both visualization and statistical tests. And we've done that using the example of a multiple regression model on a small data set. So the 6 key assumptions we've checked here are normality of residuals, linearity, multicollinearity, homoscedasticity, independence of error terms, and leverage and influential plots. Okay, hopefully I broke that down over 6 videos because it was a lot of content, and one video about this would have been awful to record and probably awful to sit through for anyone. So hopefully this was interesting and useful, and thank you for watching and listening.